Oh, by the way,
Uh,
are you,
okay. Okay, I'm back.
are you back? Okay.
Okay, then. Assalamu alaikum wa rahmatullahi wa barakatuh, and welcome to today's edition of the VOC Matric Revision program. And today we are covering physical science. So if have taken up the subject and you are in grade 12 now, this session is most definitely aimed at assisting you to help with your revision. So remember that if you have any questions, you can always send those questions through to us, and hopefully we can, cover that, inshallah. My guest today is Muntasir Kadri, who is a private tutor with Intune Tutoring, and if you in the description we actually have the link where you can access some notes, inshallah. So we welcome you to this platform, and I hand over to Muntasir.
Okay, shukran. Okay, assalamu alaikum, everybody. So today we will be covering paper 2 of physics. We'll be going over some organic chemistry. So we'll be looking specifically at question 2 questions. And these questions cover things like your organic molecules, the different types of reactions, identifying different isomers, understanding what a homologous series is, and so on. Right, so let us jump straight into it. So question 2. Let's say the letters A to F in the table below represent 6 organic compounds. Okay, so let us go about identifying these compounds. So if we look at this compound here, they give us the structural formula. Here they give us the name of the compound. So we have 3 names and 3 structures. So what are the questions that follow these? Let's say 2.1. Write down the letter that represents the following: a hydrocarbon. So one of these we need to select is a hydrocarbon. I remember hydrocarbon is something that contains carbon and hydrogen only. So that's the biggest clue you have here. In fact, it's in the name: hydro for hydrogen, carbon for carbon. Now, if we look about, we'll see that this molecule here is the only one that has carbons in it. So this is most likely going to be A is going to be our selection for hydrocarbon. Ethyl ethanoate is actually, excuse me, contains oxygen, right? And this is why we exclude it from the selection. And we'll take a look at the structure later on for this. This is a mixture between an alcohol and a carboxylic acid, and that is going to give us a special functional group, and we'll take a look at that later on. If we look at 2,3-dibromo-3-methylpentane, right, we've got a bromine in it, and that immediately negates the fact that we're going to select that as a hydrocarbon. Polyethene. And this is an interesting one. This one only contains carbons and hydrogens as well, but as we know, this is this is due to a polymerization reaction between various ethene molecules. Okay? So if you take a look, so far we've got D as a selection and A. Okay? So if you look at the memo, you'll see here they'll give us the selection of A or D. Right, there we go. We actually pointed that out. A or D could have been an answer for this question. Right? And that's because polyethene is a molecule that looks something like this. Right? So let me just remove that highlight. There we go. Now, if we look here, polyethene will look something like that. So if you identify what ethene is, it is carbon with a double bond, right, bonded to a carbon. And it then looks something like this. Remember to ensure you follow the rule for carbon being a tetravalent compound. Tetravalent meaning it only has an option of 4 valencies and therefore can only have 4 bonds. And if you count on this carbon, 1, 2, 3, 4, and this one here, 1, 2, 3, 4 bonds as well. Right? And as we can see, if we compare the two things, scroll up, carbons, carbons, hydrogens, hydrogens, carbons, carbons, and a bunch of hydrogens as well. Okay. Now, next question. 2.1.2, a functional isomer of F. So when they talk about functional isomer, they are speaking about the functional group being different, right? So they want us to look at these molecules and determine which one would be a functional isomer of F. So if you look at this, we can see that this here is a carboxylic acid over here, right? You can see this. And how we know it's a carboxylic acid, we look at this functional group over here. Right? We were just noting this functional group here. And all carboxylic acids end with COOH. And if we look at structurally, it is this C double bond OH. And that matches with this over here. Now, to identify the functional isomer, our answer is most likely going to be E. And the reason for that is if we look at this, we can see how similar they actually are. C double bond with an O. All right? And we can see that's quite similar to this. But these are different functional groups. And if we identify this one, if my memory serves me correct, I believe this is an ester. And an ester forms between carboxylic acids and alcohols. We can just quickly do a double check. Let's just go here. Esters. And there we go. So we are correct. Right? So that is an ester. Now, we can go back here. Clear that off. All right. Now, question 2.1.3. A compound which belongs to the same homologous series as B. Well, ethyl ethanoate is an ester as well. And if we had to draw the structure, well, we can see we've got ethyl. So Michael eats. So we've got, let me just check this question. All right. And if we go here, oh, sorry, give me a second. There we go. So same as B. So if we draw this structure of ethyl ethanoate, we're going to have carbon, carbon, right? That's for our ethyl. We know we're going to have an oxygen here. We're going to have a carbon and a carbon. Right? This is going to be H, 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 H. This carbon over here is going to have a double bonded oxygen. This is H, H, and H. So this is a structure. Ethyl, the ethyl part is over here. Michael eats, so that's ethyl. And here's the ethanoate section, right? So remember that when you react a carboxylic acid with an alcohol, you will get an ester. So this is important to remember. Carboxylic. Let me just open a new page over here. So I'll show you, make it clear. So we'll have a carboxylic acid plus an alcohol will react to give an ester. And something important to note is that esters are always end with the suffix O8. They always end with this suffix. So let's look at an example, and we can actually use the one that we had here. If we look at this molecule ethyl ethanoate, let's think about how it was made. So we know we need a carboxylic acid and an alcohol. So the two things we could have, most likely we'll have ethanol. So identify that we have ethanol. And we are adding it to ethanoic acid. Now let's take a look at this reaction. So we have carbon bonded to carbon. We have our hydroxyl group. And then the hydrogens that sit around the carbons. This is ethanol. And now we're going to add it to ethanoic acid, which is a carbon bonded to a carbon, right? Remember that it's COOH, so we'll have a double bond here. Well, actually, let's do it this way around for convenience sake. We'll put it over here. We then have a hydroxyl group over here, a hydrogen, and a hydrogen. Now, what happens here? Well, we notice that we end up with an oxygen in the center. And what goes missing, what leaves to make space for the bond to form, is hydrogen, is the hydroxyl group, and this hydrogen over here. Right? And then we end up getting this molecule. Right? Let me just use more space. I'll just throw an arrow pointing down. And we end up with this molecule here. C, C, O, C. Notice it's gone. The hydrogen that was attached to this oxygen is missing, and this hydroxyl is gone as well. C, double bond O, carbon, and 3 hydrogens. All right, here we go. And now we have formed ethyl ethanoate. But what happened to these molecules? Well, they actually decided to combine together to give us water as a byproduct. And that is how you do an ester reaction, or esterification is what they call it. Right? This is basically esterification. Okay, so it's important to understand your reactions. I won't really show you the mechanism of the reaction. That will show you when you get to university and you do chemistry. They'll be going into more depth about the mechanism of the actual reaction itself. Now, and there we have basically discovered that E belongs to the same homologous series as B, and those are known as ethanoates. And we can go here to the memo and we can take a look, and the answer is E for 2.1.3, as we mentioned. Now, which one is a plastic? Well, plastics are always polyhydrocarbons, right? And this means that we have what's known as a polymerization reaction, where hydrocarbons bond on hydrocarbons extensively, and there's this continuous addition, and it creates a long chain, and that's how you end up with plastic, which is polyethene. I'm sure you've heard as well of polyester, or it's actually polyester, right? That as well is a type of material used for clothes, also made from a long chain of hydrocarbons as well. And that would mean you'd be using esters, since it's polyester. So many esters to form that type of material. And in this case, for plastic, we have many ethenes being bonded together to form this plastic over here. Now, let's just look at this in a little bit more detail. Maybe some people don't understand how even these polymerization actions even occur. So if we go over here, let me just open this board up. Open a new page here. Now, if we look at polyester, what was this one we had? Polyethene. What we essentially have is this, right? The main component that makes up this plastic is ethene. The poly part just means many ethenes. That's all it means. Poly just means many. So if we look at this, we'll have our carbon double bonded to a carbon. Okay? We'll put a dot here and a dot here, indicating that the chain is going to extend. Right? But essentially, it started off with this. Okay. Now, of course, if another carbon is going to attach, we're going to lose these two hydrogens attached here, and we'll end up with some molecule to the power of N to form polyethene. N meaning the number of polyethenes attached. So, for example, if N was equal to 4, we would have this C, okay, right? And also put a dot here, right? And this would basically be, no hydrogen there. Actually, there might be. Let's take a look. 3 bonds, okay, and each single one gets 1, and this gets 1, 2, 1, 2. Right? And this would be our polyethene if it was a chain of 4 ethenes. And we can see the chain, right? We can see here's ethene, here's well. So 1, 2, 3, 4. And this is how you identify the group that is going to be used in the polymerization reaction. Okay. So let's go back here. Now, let's say write down the structural formula of each of the following. Compound C. Okay, well, we actually just did this, right? Write down the structural formula for each of the following, and let's just take a look in the book. 2.2.1. Oh no, wrong structure. I was looking at compound C. Oh, here we go. Unfortunately, I was looking at polyethene. Compound C, 2,3-dibromal methane pentane. Okay, so let's copy this, add it to a new page. Let me just clear this off. There we go. Now, this is where your ability to name organic molecules come in, understanding nomenclature and the rules of the nomenclature. So let's take a look at this. So we have 2,3-dibromo-3-methylpentane. This 2,3-dibromo, this is telling us that we have 2 bromines attached to the second and the third carbon. So we have a bromine on the second carbon and we have a bromine on the third carbon. Di meaning 2. It's just telling us that we have 2 bromines. Okay. 3-methylpentane, the 3-methyl is telling us that on the third carbon, we have a methane molecule. And pentane tells us that the longest chain is a 5-carbon molecule that is an alkane, right? Because if it ends in ane, we know it's an alkane, and pent is for 5. Think of the word pentagon, right? It's a 5-sided shape. It's also a building, right? That also has that same shape of 5 sides. So 1, 2, 3, 4, 5, right? That is what a pentagon looks like. Right, so pent just means for 5. Now, if we go ahead and we draw the structure, we always start with the longest chain. So we work backwards from right to left. So pentane, here we go. 1, 2, 3, 4, 5. 3-methyl. Okay, so we have a methyl group on the third carbon. We can go there, attach the CH3. That's the methyl group. And 2,3-dibromo. So we know we have a bromine over here, right? And depending on which way you're going to count, whether it's left to right or right to left, right? Our number 2 and number 3 could be on either side. So let's in this case, we'll go right to left. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And on the second carbon, we have another bromine. And then that, and of course, where all these lines are, those are where hydrogens are going to go. And that is going to be 2,3-dimethylpentane. That is the structure of this specific molecule. Pretty simple, not too hard. Just follow the steps. Always go longest chain first. Identify what it is they're telling you in the structure, and then just add those pieces of information in. It's not too hard at all, really. Just a little bit of practice, and you will be good at this. And if you take a look at the memo, there we go. Okay, so they place the bromine at the bottom over here, okay, which is correct. It is a better way to do it, but you won't get marked wrong for placing the bromine on top. Right? However, it is better to have the bromine at the bottom, and this is due to something known as steric strain. Now, they don't really tell you about steric strain in high school, but just to give you an idea what steric strain is, it just basically means, I mean, if we look at this and we complete it, just to give you a better understanding, steric strain has got to do with the space around the molecules. And if we look at this, we can see there's a lot less space around here as opposed to this bromine over here. So the bromine would prefer to be next to something that's occupying less space. That way there's less strain on the molecules, because if there's strain, it actually makes the chain weaker, right? And it makes the molecule more susceptible to breaking of bonds. And that is why we'd actually end up with the bromine at the bottom. However, this wouldn't be wrong in the test because it still follows the rules and they don't expect you to know about steric strain. Okay, but it's a good idea to keep in mind if you want to have an accurate representation of the molecule. Right. Now, if we go back here, just scroll down. Oh, here we go. Next question. Right. The acid used to prepare compound B. And here we have ethyl ethanoate. And we actually discussed this earlier, right? The ethanoate is going to come from the ethanoic acid. Right? Ethanoic acid is going to be our acid that we will use. And what do they state over here? Oh, we must select an option. A compound which, no, sorry, 2.2. And there we go. Ethanoic acid. This is the structure for the compound. Let's go back here. So how do we know it's ethanoic acid? Well, we've got 2 carbons. Let me zoom in a bit. We've got 2 carbons, right? That is ethene. Ethane. We know that this functional group is for carboxylic acid. Okay? And therefore the name ethanoic acid. Remember that carboxylic acid always end with the suffix oic acid. So it's very important to know your suffixes and your prefixes. Okay. Now, the monomer used to make compound D. Compound D would be polyethene, and we actually looked at this as well. The monomer is ethene. Now, monomer means a single molecule of the entire polymer chain. Okay. And then if we say polymer, it means we have multiple copies of that monomer in the same chain. So in this case, it's going to be ethene. And if we scroll down, here it is. Here's the structure for ethene. We actually looked at this earlier. Okay. They say compound A reacts with an unknown reactant X to form 2-methylpropane. Interesting. So let's look at compound A. Compound A is this over here. Let's just copy it. Copy compound A, add it to a new page. Here we go. And they're saying that this specific molecule reacted with an unknown reactant to form 2-methylpropane. Interesting. So let's take a look at methylpropane. So of course we need to understand structures, and this is where understand different types of reactions come in. They tell us that this is reacting with some unknown compound X, and it's going to give us, if I remember the molecule, I think it was 2-methylpropane. 2-methylpropane is correct. Okay, let's go back here. And this reacted to give us 2-methylpropane. Now, longest chain is prop, it's propane. So we know it's 5 carbons. 1, 2, 3, 4, 5. 2-methyl. So we have a methyl group over here. And we can go ahead and put in our hydrogens. Here we go. Okay. Now, what could have happened here? Well, I see that a double bond broke, right? And we have 4 carbons. Is this the correct molecule? Let me check something. Something's a bit off, because how did we get 5 carbons and we started with 4 carbons? Now, unless they added a methane, then that would make sense. They did say compound A, right? Yes, they did. 2-methyl. Michael eats peanut. Oh, sorry, my apologies. I made a mistake. Michael eats peanut. Sorry, butane. Sorry, I thought this was pentane. Propane is 3 carbons. Michael eats peanut butter. Sorry. Eats peanut butter. Here we go. Yes, that makes more sense. That makes more sense. Oops, my apologies. Here we go. So I'll just show you what I was doing. So M is for one carbon. This is any methyl group has one carbon. Any ethyl, two carbons. Any propyl, three carbons. And any butyl, four carbons. And the little rhyme that I use is Michael eats peanut butter. Right? And this tells me that because M is first, it's one carbon. Because eats is second, it's two carbons. Because peanut is third, three carbons. And because butter is fourth, four carbons. And that's how I go about, just reciting this and knowing what it is that I need to do. Now, 2-methylpropane. Okay, so we know it's three carbons because it's propane. Okay, and we have a methyl group on the second carbon. Okay, and let us draw it the way it looks over here so it makes more sense. So this is C H H H, and here we have an H, an H, H, oops, and another H. Now let's see what happened. So what broke here? Well, we can see that a double bond broke. And this double bond broke. So remember, we know that bonds consist of two electrons interacting with each other and sharing the same valency. So what essentially happened here was this bond broke and it decided to say, hey, you know what? I'm going to break this bond and I'm going to send a spare electron to chill over here. And that's what happened. This bond basically broke. And one of the electrons broke off from here. So we know, for example, I'll just give you an idea. Here we have carbon, carbon, right? We break the bond and then we actually end up distributing, let's say, one of the electrons there and one of the electrons there. So now these electrons are unpaired and therefore they need to pair with something else. Okay, so we know this bond broke. A electron moved here and one electron decided to move here as well. Okay, so if we look at the structure, oh, sorry, I forgot to put a hydrogen in over here. If we look at the structure, what's different? The bond is missing, but what else is added? Well, if we look at the central carbon or the chiral carbon, we'll see that a hydrogen was added. Oh, look at this. There's a valence electron, which means the hydrogen came with its own electron and decided to place itself there and they formed a bond. There's no hydrogen here and there's a hydrogen here. Well, guess what? Another hydrogen came. Now, if we think about it, we've added hydrogen. So that kind of answers our question as to what we added. Well, we've got two hydrogens. Hydrogen exists in nature as a diatomic molecule. As H2, diatomic means two atoms. It exists as this. And what we actually underwent was hydrogenation. And what we did was we add, and it's an addition reaction where we add hydrogen to an alkene and we turn it into an alkane. And that's essentially what we did here. And let's check the memo and see if we are correct. So we go here. And here we go. Addition or hydrogenation. And the missing molecule that we were supposed to use in the reaction was hydrogen. So we are actually spot on and we were on the right track there. Okay, so that's perfect. That makes everything a lot easier. Okay, now let us look at another question too quickly before we end the session. Let's just see. Let me pull another exam up for us. Grade 12. Let's maybe look at, not 2016, let's look at 2017. Paper 2, let's just pop this one up. Here we go. Okay. Here we go. Okay. So we'll look at question 2 again. Let's just scroll down. Okay, this is all the multiple choice. And here we go. And now we're along the same lines again. So let's take a look at this. Question 2. Study the structural formula below. This looks familiar. This is a ester. It's between an alcohol and a carboxylic acid. So which homologous series does this belong to? Well, we can immediately say that this belongs to esters. Okay. What is the IUPAC name? Let's identify the name. Right. So we know that esters end in the suffix -08. The -08 part is this part over here, which used to be a carboxylic acid. So this is Michael eats. So we can say ethyl 1, 2, 3, 4. Michael eats peanut butter. So that's 4. So that's bute. And this is going to be ethyl butanoate. Right? That should be the answer. Let's check if we are correct. Let me just pull up the memo. Okay, just pull that across and scroll down. And there we go. Ethyl butanoate is the correct answer. And we see esters for the first functional group. Okay, now let's go on to the next one. So 2.1.3. Name of the organic acid used in its preparation. And the way we identify what organic acid we used is we look for the molecule with the C double bond O. And this entire thing tells us what carboxylic acid was used. And that would be butanoic acid. Remember, carboxylic acids always end in oic. Right? Now, structural formula of its straight chain. Structural formula of its straight chain unbranched functional isomer. Straight chain unbranched. Let's take a look at what they're actually asking here, because I'm actually not too sure. Unbranched straight. Oh, so okay. So straight chain, they mean that these carbons are all linked and there's no break in between the chain. Because as you can see here, here's 4 carbons and here's 2 carbons. And if you take a look at the memo, you'll see that they'll put the carbons together and they'll just move the carboxylic acid to the end, and that will give you the structural formula of its straight unbranched isomer. We can take a look at how we do that. So what we'll do is we'll just put the C double bond OH at the end. Let's see what they did here in the memo, which is most likely the case. And there we go. They put the C double bond OH at the end, and we can see that we have 1, 2, 3, 4, 5, 6 carbons. That's all they did. Okay? And if we go here, 1, 2, 3, 4, 5, 6. And that's all they did. They just rearranged the chain so that all the carbons are together, and then the carboxylic group goes at the end of the chain. So essentially what we're busy making is pentanoic acid is what we end up making because of the 5 carbons. Now, 2.2. Write down the structural formula of 4-methylpentanetone. Now, this is a ketone. And we need to know what the structural formula for a ketone is. Right? Because obviously it's a specific functional group. So if we take a look at what ketones are, once again, this is where identifying your functional groups is very important. And if we look at a ketone, here we go. So for ketone, it's a double bonded O, and then we have a odd group on the one side and another odd group on the other side. And what does this mean? The R just means that any carbon chain is attached to either side of it. That's all it means. Okay, so now if we go back to this problem, so 2-methylpentone. So we do know that the functional group is this, and this is why it's so important to know them. So we know the longest chain is pent, right? and we have a methyl group on the fourth carbon, and the ketone is on the second carbon. So essentially what they're telling us is this. We have 1, 2, 3, 4, 5, right? And we can go 1, 2, so the ketone is over here. Let's just call this carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. The double bond O goes over here. Okay. We have a methyl group on the fourth carbon, CH3, and that's it. And hydrogens go everywhere else except over here because we already have 4 bonds. So we should end up with hydrogens like this. Another one here, another one here, 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 and here. And that is it for 4-methyl pentan 2O. And there we go. Right. So so that's pretty much it for today. Right. We kind of ran out of time to cover the rest of this paper. But I hope it has been helpful and that you have a better understanding of how to identify functional groups and how to draw the structures of various molecules. And this, of course, takes practice, and you'll just need to continue going over it. Okay, so thank you so much, and I hope you enjoy the rest of your day. Assalamu alaikum.
Walaikum salam wa rahmatullahi wa barakatuh. Shukran once again to you, Muntasir, for joining us today. We will be having you back on tomorrow for our session on maths from myself, Konita Kamar, and my guest, Muntasir Kadri. We bid you farewell. Assalamu alaikum wa rahmatullahi wa barakatuh.